we talked about equilibrium, and equilibrium simply means that the sum of the torques, which we know are the force times the moment arm, so a torque in the counterclockwise direction translates with the right-hand rule. We put our fingers in the direction of the force and we rotate them into the radius. So a force acting up, rotated into the radius, gives us an outward torque. So the torque is not in the direction of, not on the paper, it comes out of and into the paper. So here we have a bridge, and we're going to, for equilibrium, we want the sum of the torques to equal 0, and the sum of the forces up and down to equal 0. Otherwise, the object would not be in equilibrium, it would move. If the forces in the downward direction were greater than the forces in the upward direction, the bridge would collapse. If the opposite were true, the forces up were bigger, it would move up. And if the torques were not balanced, the bridge would rotate. None of these things is true. Therefore, we want the sum of the torques and the sum of the forces to be 0. And I have a bridge of length L and mass M. And it is of uniform construction, so the center of gravity of the bridge is in the middle. And we have a car somewhere on the bridge that has some little m times g for its weight. So these are the two weights, and they must be supported by these two upward forces on the supports. So this force upward on support A and this force on support B, marked FA and FB, must sum up to be the downward forces, mg, the weight of the bridge, and mg, little mg, the weight of the car. And now it's time to talk about the torques. The sum of the torques must be 0, and the torque is the force times distance. You have to pick a point. It doesn't matter which one. Pick a point about which all torques in the problem will be measured. I picked A. Why did I do that? Because now this force will not create a torque because it acts through the center of rotation and can't create a torque. So I've taken this force out of the picture, so to speak, in the torque equation. So here is an upward force on the bridge. The force is FB, the length is L, the torque is out of the page. So this torque is out of the page. And we have this force times this moment arm, and that would be into the page. So it gets a minus sign, and this torque is half of L, half the length of the bridge is the force, into the moment arm, L over 2, mg gives us another minus sign because it's out of the page. So the sum of all the torques, 1 plus torque and 2 minus torques, sum up to 0. Please notice that in this equation, the sum of the torques, only FB is unknown. So we can immediately solve using algebra for the force that support B has, which is 3/4 of mg. It supports 3/4 of the car. Maybe that makes sense to you because this is 3/4 of the way over. So 3/4 of the force is handled by FB, and half, because this is halfway between the two supports, that this support, FB, upward force to hold the bridge in place, must support half the weight of the bridge. So FB is found immediately, and we can substitute into this equation where the only unknown is FA, because we move FB to the other side, which I have done here, and find that FA, after a little bit of algebra, is half of mg plus 1/4 of little mg. So FA is supporting half the bridge and only 1/4 of the car, because the car is far away from this support. It's 3/4 of the way out. So it supports only 1/4 of the weight of the car and half the weight of the bridge. So we're able to say that in order for equilibrium to exist, in order for the bridge not to be moving, translating, or rotating about any point, the support forces upward, shown in green, must be these two values. And so that is the sum. The two forces give this upward sum of forces. And when you add these two up, you will, of course, get the weight of the bridge and the weight of the car, because those are the only downward forces acting on the bridge. So there is an example of an equilibrium problem. The secret is to pick a pivot point through one of the unknown forces, which will take it out of the picture in the torque equation and allow you to solve for the other force directly. Once you do that, you plug it into the force equation, and both forces have been found, establishing the equilibrium condition that the sum of the torques must be zero and the sum of the forces must be zero. Watch your signs, SIG and S signs. In this case, I have defined up to be, how did I define up? I defined up to be positive, and I defined down to be negative, and I defined counterclockwise torques to be positive and clockwise torques or negative. So it's important to set up your sign convention before you begin the problem so that you do not make an algebraic error.